This wave machine was developed by a science teacher in Singapore, collaborating with a local fabrication laboratory to develop a mechanism to demonstrate wave motion. We've refined the initial wooden prototype in the Make to Learn laboratory at the University of Virginia to create an enhanced version. This version consists of a series of 12 cams. It can be difficult to understand the underlying mechanism by looking at all 12 cams at once. Therefore, we created a physical model consisting of a single slice of the wave machine. This simulation is a digital version of that physical model. This model consists of two parts, a rotating cam and a cam follower that follows the motion of the cam. There are several behaviors of the cam that can be observed. As we rotate the cam follower has a maximum height of 100. And as we go on around to make a complete rotation, it has a minimum height of minus 100. Once we come back to a full rotation and are at 0 degrees again, the cam follower is at the midpoint between the maximum height and the minimum height. The center of the cam, shown as a blue dot, rotates around the pivot point, and it creates a circle. We can demonstrate this by graphing the path of the center of the circle. So as we go around the pivot point, we can trace out the path of the center of this cam, and we can see that it does in fact make a circle around the pivot point. So consequently, we would expect that if we graph the motion of the center of the cam, it would generate a waveform, and that waveform would give us a shape that looks something like this. That would be exactly what we would expect because the path is a circle, and therefore we would expect the associated waveform when we graph that motion. Now, we could also observe that the separation between the position of the cam follower and the cam center below it is always 150. So when the cam follower is at 0, the cam center is at a minus 150. Now when we are at the maximum height, the cam follower is 100, and the cam center is minus 50, so the separation is still 150. Once we rotate around to 180 degrees, we're back at 0 and minus 150. And then finally, when we're at the minimum height, the cam follower is minus 200, and the center of the cam is minus 250. So we still have that same separation. So the cam is essentially transposing its motion onto the motion of the cam follower. As a result, if we graph the vertical motion of the cam follower, we're going to expect that it also will create a graph that follows the same path as the path of the center of the cam, and it is separated by the radius of the cam. So these characteristics are used by engineers to cause the cam follower to follow a prescribed path. These particular examples results are only valid for a cam that's a circle. The path followed by a cam follower would be different for a cam that was a different site, such as an oval. Our engineers use this characteristic to shape the movement of the cam follower. Cams are found in many different kinds of machines. For example, cams lift the valves in a car engine to allow gas to enter the cylinder, and also lift another valve to allow the exhaust to escape the cylinder. This model illustrates how cams can also be used to create machines for science demonstrations.